Doggerland, Beringia, Zealandia. What do these sunken continents really hide? Dear traveler, greetings. Today we unveil three forgotten lands, engulfed by time and tides: Doggerland, Beringia, and Zealandia. Once, they housed deep forests, living plains, and creatures of which we sometimes know only the bones. In Doggerland, between the British Isles and Europe, echoed the footsteps of strange beasts and the voices of ancient peoples. Who were they? And what became of their worlds, drowned without a sound? On the icy lands of Beringia, giant herds roamed the cold. Mammoths, saber-toothed tigers, and men clad in skins, crossing a bridge now broken by the ocean. As for Zealandia, hidden beneath the Pacific waters, what biological mysteries did it hold? Isolated life forms, creatures whose names we don't even know. These continents have disappeared, but their secrets have never stopped whispering. But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a nice trip. Since the dawn of time, our planet has seen immense continents come into existence and break apart, profoundly disrupting the evolution of life and landscapes. Among these upheavals, the formation of the supercontinent Gondwana stands out as one of the most significant. Its assembly was completed about 520 million years ago, or 323 million miles, at a time when marine life was just beginning to diversify. Gondwana then united most of the land masses in the southern hemisphere, South America, Africa, Antarctica, Australia, as well as fragments that would later form present-day Zealandia. The history of this vast continent sheds light on the tectonic mechanisms that shape the Earth's surface. Under the influence of the mantle's internal forces, portions of the crust slowly fused or drifted. In Gondwana, the future Zealandia was probably located in the southwest, near the current Australian coast. According to researchers, this region experienced several episodes of accretion. Crust fragments or small continents gradually attached themselves, helping to reinforce the overall mass of Gondwana. Over geological eras, sedimentary rocks slowly accumulated, drawing a complex underground history. Between the Permian and the end of the Jurassic, thick layers were deposited in marine and continental basins. Composed of clays, sandstones, and silts, they are valuable to geologists. Indeed, they contain fossils and clues of ancient environments. The extent of these deposits shows that vast areas of Gondwana, including the region corresponding to present-day Zealandia, offered ideal conditions for sustainable sedimentation. These successive layers provide a precious testimony of ancient climates and environments. In the Permian, then during part of the Triassic, vast regions of Gondwana were still experiencing a cool climate, a legacy of the Carboniferous glaciations. Gradually, temperatures rose, humidity set in, and vegetation thrived. Vast forests of arborescent ferns and primitive conifers spread out, leaving their fossil traces in the sediments. By analyzing these strata, paleontologists today can trace the evolution of the biosphere and better understand the dynamics of the planet in that distant era. Among the notable plants of this era, the glossopterids held a central place. Related to seed ferns, they were distinguished by their large, robust leaves. These plants thrived during the Permian, when Gondwana extended into the southern hemisphere. At that time, sea level variations created marine passages across the continent, gradually altering connections between regions. These water arms facilitated the dispersion of certain aquatic species, while gradually isolating plant ecosystems. As a result, glossopterids developed characteristics unique to each region, marked by this natural isolation. To understand this phenomenon, imagine vast forests traversed by thin saltwater intrusions. At times, the drifting of continents or melting of glaciers altered sea levels, widening or shrinking these marine passages. Some plants then found themselves isolated in restricted areas, which favored the emergence of genetic traits unique to each region. That's how several varieties of glossopterids, specific to small areas of Gondwana, appeared. This rise in endemism enriched biodiversity and already prepared the first fractures that would, much later, separate these lands in the Cretaceous. This first phase of evolution reveals the complexity of the mechanisms that shaped our planet. Research conducted in the ancient regions of Gondwana provides essential insights into the progressive integration of the Zealandia region. Layers of sedimentary rocks preserve the trace of successive deposits and extinct species. Thanks to these clues, researchers trace back in time and reconstruct step by step the major geological, climatic, and biological upheavals that shaped the Zealandia we know today. Between 84 and 60 million years ago, the continental mass of Zealandia progressively detached from Antarctica and Australia. This movement was part of intense mantle activity, dominated by the Kerguelen superplume, a vast reservoir of heat and magma under the Earth's crust. This phenomenon encouraged the opening of fractures and the formation of the Tasman Basin. The lithosphere stretched, giving rise to new oceanic spaces and marking the birth of a continent in its own right. This process marks a major turning point in the geological history of the region. A superplume refers to a gigantic plume of hot rocks rising from the Earth's mantle. In the case of Kerguelen, this flux of magma exerted constant pressure beneath the crust, causing the appearance of cracks. Through these faults, incandescent material seeped in, giving rise to volcanoes and large lava flows. In some places, the crust was even temporarily uplifted. Vast sheets of basic rock, called basaltic flows, then spread out, forming massive volcanic plateaus still visible today. They bear witness to the profound upheavals that marked this era. The opening of the Tasman Basin results from this prolonged stretching of the Earth's crust. As it distended, its thickness sometimes decreased from several tens to only about 20 kilometers or 12 miles. This significant thinning, indicating a stretching of over 200%, shows how far the plates diverged. Gradually, seawater flooded the subsided areas, giving birth to a new ocean basin. In this unstable context, some landforms briefly formed before collapsing, according to the many fractures that traversed the region. The alkaline volcanism, rich in sodium and potassium, gave rise to vast, dark, and very fluid basaltic flows. These lavas, low in silica, sometimes extended over kilometers or miles. They formed large shield volcanoes in some places, and small vents scattered on an already weakened crust in others. With each eruption, the landscape was reshaped, leaving new rock layers and altering soil chemistry. Even today, the volcanic plateaus visible in the region bear the mark of these ancient magmatic upheavals. Under the pressure of magma, some areas were briefly uplifted, then lowered by tectonic movements. This back and forth sculpted an unstable landscape between ephemeral massifs and shifting plains. The biosphere constantly had to adapt to these changes, between temporary emergences and returns of the sea. The forests already housed ancient conifers and varied ferns, while small reptiles explored these nascent lands, sometimes quickly submerged again by the ocean. Overall, the warm and humid climate favored the development of life on the emerged lands. Heavy rains enriched the soils by depositing minerals and nutrients. Subtropical forests, dense and rich in pioneer species, gradually settled. The high carbon dioxide levels in the air strongly stimulated photosynthesis, reinforcing this vegetative dynamic. As the seas around Zealandia widened, the region began to differentiate ecologically from its southern neighbors, initiating a gradual and enduring separation. Geological analyses reveal the extent of the crust's stretching. In some areas, it expanded to more than double its initial size, becoming significantly thinner. These data are confirmed by oceanic drilling, whose rocks show chemical signatures indicating intense mantle upwelling. The Kerguelen superplume, in causing this stretching, also allowed immense volumes of magma to reach the surface, forming vast layers of basalt up to the continental margins. This profound upheaval was accompanied by visible transformations on the surface. As new seas appeared, warm marine currents flowed through them, promoting species migration. Sediments today bear the trace of this, as do the first coral reefs in formation. On land, the alternation between uplifts and subsidence created distinct ecological zones. Some highlands still hosted fauna inherited from Gondwana, while others were already isolated by the ocean. Gradually, a mosaic of varied landscapes emerged. Throughout this separation, the Kerguelen superplume played a key role. Its heat surges intensified magma upwelling, causing fracturing and occasional uplifts. Geologists identify these episodes through basalt composition, signs of rapid cooling, and the magnetic imprint preserved during lava solidification. These clues allow the reconstruction of a scenario of gradual detachment guided by powerful internal forces. When imagining the first Zealandia reliefs emerging from the marine depths, one envisions a vast landscape dominated by high mountain ranges. Composed largely of feldspathic rocks, rich in feldspares, common light-colored minerals, these cordilleras are the result of repeated tectonic uplifts. Some ridges, sometimes covered with seasonal snows, formed a continuous backbone across the young continent, shaping basins and naturally guiding river courses. These cordilleras, covered with conifers and ferns adapted to altitude, formed rugged relief. Further down stretched wide valleys, carved over time by erosion into very ancient rocks. Rain, frost, and landslides shaped steep slopes and deep gorges there. The sediments torn from the mountain were carried to the coastal plains, where they gradually enriched the soils, preparing the formation of future marshy areas. At the foot of the mountains, vast coastal plains, sometimes stretched for hundreds of kilometers or miles, forming a gentle transition to the sea. Water-saturated, these areas took on the appearance of swamps, where stagnant water created an ideal semi-aquatic environment for specific flora. Reeds, rushes, and other aquatic plants proliferated there, playing an essential role in natural water filtration and sediment retention. In these marshy plains, the flow of rivers deeply transformed the landscape. Most of these waterways, oriented from north to south, followed the natural slope of the mountains. Fed by rain, snowmelt, and the proximity of the ocean, they carried large loads of silt. By flowing into the Proto-South Pacific, they gradually shaped new coastal areas and vast estuaries, progressively structuring the emerging geography of Zealandia. Higher up, between the ridges and valleys, ancient intramontane lakes, called paleo-lakes, formed. These basins, sometimes born from terrain collapse after tectonic activity, varied in size, some modest, others extending over several tens of square kilometers or miles. Their tranquil waters accumulated sediments and organic materials, depositing precious strata over time. Each layer preserved clues about the fauna, flora, and climate of the era, making these lakes true natural archives. On the shores of the Paleo Lakes, in a humid and temperate climate, the vegetation was particularly diverse. Among the dominant species were the Podocarpaceae, conifers typical of the southern hemisphere. Adapted to different precipitation regimes, these trees, often with narrow leaves, thrived thanks to their deep roots, which drew nutrients from waterlogged soils. Protected by a dense forest canopy, they found ideal conditions to develop widely. Tree ferns added a majestic touch to this dense vegetation. Their stipe, a kind of trunk that can reach several meters or around 10 feet, bore large fronds arranged in a crown. In these ancient forests, light filtered through the foliage, creating a humid microclimate ideal for spore germination. The whole scene evoked current tropical forests, where humidity is maintained thanks to ambient heat and the dense shade of interwoven foliage. From mountaintops to marshy areas and passing by paleo lakes, these biotopes formed a true sanctuary of life. Soils rich in organic matter and minerals stimulated dense vegetation. Trees, ferns, and moss thrived thanks to constant humidity, while the undergrowth sheltered insects and small animals. Large herbivores, if present, would probably have frequented the lake shores to drink, thus contributing to seed dispersion and the dynamism of these burgeoning ecosystems. These emerged lands formed a unique landscape where tectonics, erosion, and sedimentation balanced with finesse. The feldspathic cordilleras structured the territory, directing the waters and influencing the distribution of life. Below, the marshy plains collected inputs from above, while the paleo lakes preserved the memory of natural cycles. This diversity of environments, graduated according to altitude and proximity to the ocean, nourished a teeming biodiversity. At the dawn of Zealandia's history, this contrasting relief already foreshadowed an exceptional destiny, that of a continent shaped to become a cradle of unique species. In the late Cretaceous, Zealandia enjoyed a stable subtropical climate, with temperatures around 25 degrees or 77 degrees all year round. Rainfall often exceeded 3,000 centimeters or 118 inches per year, maintaining constant humidity that favored a lush and dense flora. The atmosphere then contained nearly 1,000 ppm of carbon dioxide, much more than today, creating an intense greenhouse effect. The seasons were scarcely marked, with little variation in temperature or precipitation. Thus, Zealandia presented itself as a warm, humid, and intensely vegetated world. No trace of glaciation marked this era. The poles were ice-free, and warm oceans dominated the planet. The high sea level favored evaporation, leading to abundant rains on Zealandia, which continually nourished forests and flooded plains. In this stable climate, vegetation grew year-round, without a resting season. Giant ferns, tropical conifers, and archaeology formed vast humid forests, offering a fertile refuge for a fauna perfectly adapted to these generous conditions. Among the most striking formations of this era were lateritic soils. The abundant rains leached the upper layers, carrying away soluble elements and leaving behind resistant compounds like iron and aluminum, responsible for their characteristic red hue. This process revealed a warm and humid climate, persisting for long periods. Under these conditions, bauxite, rich in aluminum hydroxides, was gradually formed, a concrete testament to the intense chemical alteration affecting Zealandia's emerged soils. This warm and humid climate favored abundant and varied vegetation. Tropical forests extended widely, populated with subtropical conifers, tree ferns, and primitive flowering plants. The undergrowth teemed with insects, invertebrates, as well as mosses and epiphytes clinging to the trunks. In this stable environment, many species specialized in precise niches, giving rise to endemic life forms. Water, omnipresent, sculpted the relief by creating fertile valleys and marshes, where aquatic plants adapted to the dense shade of the canopy thrived. Herbivorous dinosaurs, like small, primitive mammals, benefited from an environment rich in food and shelter. Dense forests and giant ferns supported a thriving food chain. The absence of marked seasons allowed many species to reproduce year-round, without climatic constraints. Although rare, fossils confirm the presence of dinosaurs and mammals unique to the region. In this water-saturated ecosystem, survival depended less on the fight against cold than on adaptation to a humid, teeming, but demanding environment. Persistent heat and constant humidity led to significant weathering of rocks. Tropical rains decomposed the bedrock, releasing minerals and metals. Aluminum, with its low solubility, accumulated in the lateritic layers, forming bauxite deposits that mark an ancient, very humid climate. On the slopes and plateaus of Zealandia, this phenomenon of laterization reflects continuous erosion, characteristic of an ice-free environment, quite different from what we know today. In the absence of winter cold, vegetation remained active year-round, continuously accumulating carbon. Large quantities of organic matter accumulated in the soils, feeding fungi, bacteria, and invertebrates. These decomposers transform this biomass into essential nutrients for plants. Rivers, loaded with sediments, transported minerals and organic matter to the coastal plains. This dynamic reinforced the fertility of the land, helping to shape the lush landscape of Zealandia. Thermal exchanges between warm oceans and the atmosphere maintained a stable climate. The surface waters released their heat in the form of vapor, enhancing the greenhouse effect already fueled by a high carbon dioxide level. In the absence of ice caps, the sea level rose, flooding low plains and sometimes connecting lands that were once separated. In this world of limited but verdant lands, terrestrial and marine life flourished. We can easily imagine shores lined with primitive mangroves, where estuaries abounded with life forms adapted to the perpetually mild climate. When Gondwana still housed the lands of the future Zealandia, animal life thrived in humid forests, bathed in a subtropical climate. Before the supercontinent broke apart, a varied fauna occupied these changing landscapes. Flat-snouted herbivore dinosaurs, bipedal predators, arboreal mammals, and giant insects. Embedded in ancient rocks, their fossils testify to a fascinating world where adaptation and the struggle for survival were already shaping the early forms of Zealandian biodiversity. Among the most impressive inhabitants of this era were the hadrosauriforms, nicknamed duck-billed dinosaurs due to their distinctive jaw. Herbivores, they had long rows of teeth arranged in complex batteries, ideal for grinding tough vegetation like ferns or primitive conifers. They probably lived in groups and roamed vast territories in search of areas rich in tender plants. While complete skeletons remain rare in Zealandia, numerous footprints found in sediments confirm the presence of several lineages, some of which reached over 10 meters or 33 feet in length. Fossil footprints also reveal the presence of formidable predators, akin to neovenatorid theropods. These bipedal dinosaurs, with powerful hind legs and short arms, use their long tail as a counterbalance when running and attacking. Their strong jaws, filled with sharp teeth, allowed them to severely injure their prey. Although smaller than the famous tyrannosaurs, these agile hunters roam the same dense forests and wetlands as the herbivores. They stalk their targets at the forest edge or near water points, often taking advantage of surprise to capture their prey. Herbivores and carnivores coexisted in a vegetation-rich environment, nourished by a warm and humid climate. Abundant rains promoted rapid plant growth, providing food and shelter to many species. Marshy areas served as refuges, including for incubating eggs. The muddy soils, regularly flooded, have preserved footprints that, millions of years later, allow researchers to reconstruct the movements and lifestyles of these ancient giants. The climate, mild and stable, translated into temperatures close to 25 degrees Celsius or 77 degrees, and regular rains throughout the year. Sediments reveal a subtropical environment ideal for dense vegetation. Primitive conifers, tree ferns, and seed plants thrived around swamps teeming with insects and amphibians. The constant humidity and absence of frost created perfect conditions for a diversified food chain where dinosaurs, mammals, and invertebrates coexisted in balance. Apart from dinosaurs, geological records reveal the presence of small mammals called multituberculates, named for their teeth equipped with numerous cusps. This complex dentition allowed them to gnaw seeds, hard fruits, and possibly even insects, indicating a very flexible diet. Some likely lived in the canopy, using their claws to climb and escape predators. Fragments of jaws found in ancient forest soils show that they adapted well to humid forests, where arboreal life offered them a refuge from ground competition. Before the isolation of Zealandia, traces of primitive marsupials were also found, small omnivores with pointed snouts and sharp teeth, capable of feeding on insects and forest fruits. Already equipped with their famous pouch, they would explore the ground in search of food or shelters, although they were less diverse than their Australian descendants. Their fossils, found alongside those of arboreal multituberculates, reveal a typical community of small Gondwanan mammals, well adapted to the humid forests of the time. In the undergrowth and around dead trunks lived surprising invertebrates. Among them, large saproxylic beetles feeding on decomposing wood played a key role in recycling organic matter. By digging galleries in the rotting trunks, they sped up decomposition and released essential nutrients to the surrounding flora. This silent but vital work contributed to the renewal of forest soils, supporting a dense vegetation from which herbivorous dinosaurs benefited directly. In contrast to the massive beetles, stick insects embodied the art of camouflage. Their bodies perfectly mimicked a branch, a leaf, or a piece of bark, making them almost invisible to the eyes of predators. Some species had barely visible antennae and wings resembling nibbled leaves. They lived in the canopy, feeding on tender leaves or young shoots. Their presence testifies to the richness of the forest ecosystems of the time, where each species, through strength, speed, or stealth, found its own strategy to survive. Before the breakup of Gondwana, the future Zealandia was an integral part of a rich and vibrant world. The fossils discovered, dinosaur footprints, jaws of small mammals, fragments of giant insects, tell the story of a land where life displayed astonishing creativity in a lush environment. Isolated from neighboring continents, these ecosystems gradually shaped an original fauna, precursors of the endemism that would mark Zealandia. By exploring these remains, we dive into a fundamental chapter of evolution, one where geology was already beginning to shape the distribution of species on a living scale. Between 60 and 25 million years, Zealandia began a slow submersion, marking a decisive turning point in its geological history. After the rifting phase that had already weakened the crust, the region underwent thermal subsidence. As it cooled, the lithosphere gradually sank. It is estimated that the continent lost an average of 1,500 meters or 4,221 feet of altitude, with marine waters gradually covering its lands. This progressive immersion significantly reshaped the face of Zealandia. This slow subsidence is explained by the Earth's internal cooling. After the opening between Zealandia and neighboring masses, the lithosphere, this rigid layer forming the Earth's surface, began to stabilize. As it cooled, it became denser and gradually sank into the mantle. Over tens of millions of years, this movement reshaped the relief, with coastlines receding and vast expanses of land slowly being submerged. As Zealandia's altitude decreased, the neighboring seas gradually spread into the lowest plains. This phenomenon is known as marine transgressions, which refers to the progressive rise of sea levels relative to emerging lands. In these newly flooded areas, thick layers of sediments accumulated. These deposits, described as glauconitic, contain a clay-rich mineral with iron and potassium, glauconite. Its presence indicates shallow, calm, and well-oxygenated waters, a sign of stability in the marine conditions of the time. With the continued subsidence, the sea kept encroaching on the land, leading to a new phase of sedimentation. This time, limestone-rich and nanofossils began to deposit, tiny remains of unicellular algae suspended in the water. These microorganisms, mainly composed of calcareous plates called coccoliths, indicate high biological productivity in these shallow seas. Slowly accumulating on the ocean floor, these calcareous debris gave rise to thick rock layers. Today, these formations are still visible in samples from scientific drilling conducted on the submerged continent. For terrestrial fauna and flora, these marine transgressions had a profound impact. As plains disappeared beneath the waters, vegetated areas drastically diminished. The conifer and fern forests, once thriving on damp soils, retreated to the remaining high plateaus. Animal life also had to concentrate in fragmented territories. This isolation fostered the emergence of endemic species, originating from populations separated by the new natural barriers. In this changing landscape, the emerging lands fragmented into a vast archipelago. The mountain ranges remaining above the waters became refuges for biodiversity, while ancient land corridors were replaced by sea channels. This fragmentation accelerated the formation of new coastlines and created a mosaic of coastal environments, sheltered lagoons, wave-battered cliffs, ephemeral beaches. Every nook offered a unique microhabitat, paving the way for the emergence of species perfectly adapted to these changing niches. Scientists confirmed this archipelago fragmentation by studying underwater cores and sediment samples. The analysis of fossil pollen allowed them to reconstruct the ancient distribution of vegetation on these shifting lands. Some pollen from endemic ferns, for example, are found in layers dating from environments now submerged. These discoveries demonstrate how coastal erosion, the gradual disappearance of emerged soils, and increasing competition for resources have profoundly influenced the life of plants and animals on a continent in full decay. Climatically, the period from 60 to 25 million years ago was generally warmer than our present time. Temperatures could reach up to 25 degrees Celsius or about 77 degrees in some regions, with heavy rains nourishing vast forests. Yet, this warmth did not prevent the sea from advancing. Oceanic level fluctuations, linked to tectonics and water volumes in basins, caused a gradual inundation. The local fauna had to adapt, or slowly disappear. In these scattered island environments, the ecological pressure intensified. The forests, confined to the heights, sheltered a great diversity of pollinating insects and small reptiles, taking advantage of the numerous available niches. Birds, capable of flying from one island to another, played a key role in seed dispersion. Conversely, larger mammals, requiring vast territories, suffered from habitat reduction. This period marked a profound reorganization of life, completely reshaped by a geography in perpetual transformation. Around 25 million years ago, the submersion of Zealandia reached its peak. Most of its land vanished beneath the water, leaving only a few islets and mountain chains. Marine sedimentation continued, filling the basins and outlining a complex geological mosaic. Today, the underwater reliefs around New Zealand still bear the trace of this history. Slow and silent, the immersion of this forgotten continent remains etched in the rock, revealing the fascinating plasticity of our planet. Over the geological ages, the fragmentation of lands has favored the emergence of a unique insular fauna. The moa, now extinct, and the kiwis, still present, are striking symbols of this. In the absence of mammalian predators, these birds evolved without major constraints. The moa, unable to fly, occupied diverse habitats, from forests to plains. Some exceeded 2 meters or about 7 feet in height, while others stayed discreet under the vegetation. Their varied diet made them highly adaptable. But this prosperity ended with the arrival of humans, who caused their extinction. Kiwis, much smaller than moa, have also lost the ability to fly, but for different reasons. Adapted to life on the ground, they probe the earth with their long, sensitive beaks, searching for insects and worms, mainly at night. Their excellent sense of smell and the absence of functional wings illustrate how insular isolation has guided their evolution in an environment without real danger. In the remaining rainforests, the majestic Araucariaceae endure. These ancient conifers, recognizable by their branches arranged in regular whorls, thrive in a humid and mild climate, around 20 degrees or 68 degrees. Their thick bark offers natural protection against seasonal variations. They embody a living vestige of a time when these trees dominated vast landscapes across the globe. In the damp understory, epiphytes abound, notably bryophytes, mosses, and liverworts. Clinging to trunks and branches, they live without parasitizing their host, absorbing moisture from the air rather than the soil. Adapted to the shaded canopy, they retain water and stabilize the microclimate. These green carpets provide shelter to tiny invertebrates, further enriching the complexity of these forest ecosystems. With the fragmentation of lands, the large saurians gradually disappeared. These giant reptiles, which once dominated Gondwana, required vast territories to survive. But insular isolation reduced their spaces and resources. Unable to adapt, they became extinct, leaving a vacant niche. Birds, free from this competition, then managed to establish themselves at the top of the food chain, without major terrestrial rivals. It is a striking example of endemism. Unique species, like moa, kiwis, or certain ancient plants, evolved in isolation for millions of years. The absence of predators and a stable climate shaped unique traits in them. Today, only the kiwis remain, silent witnesses of a bygone past. Moa, on the other hand, disappeared shortly after the arrival of humans. In the end, insular evolution offers us a fascinating spectacle. On these isolated lands, birds have occupied all the free niches, taking advantage of the absence of large predators. Endemic conifers and discrete epiphytes also tell a story of silent adaptation. Devoid of the continent's laws, nature invented its own rules. Each species, each plant, embodies a unique response to a singular environment. These islands have become true living laboratories where life, freed from conventional pressures, has dared to reinvent itself with boldness. Understanding these dynamics is to appreciate how geographical isolation and the absence of large predators have favored unique evolutionary trajectories. Without the pressure to flee or defend oneself, some birds have lost the ability to fly. Conifers have colonized the misty canopies, and bryophytes have thrived on every available surface. These adaptations tell a fascinating story, that of life constantly inventing whenever constraints change. Preserving these relic species means protecting precious witnesses of this living plasticity and nature's capacity to reinvent itself in isolation. Zealandia is a continent almost entirely submerged in the South Pacific. Only New Zealand and a few neighboring islands emerge, representing a tiny portion of its vast extent. Geological surveys, however, reveal the presence of three major plateaus: Campbell, Chatham, and Lord Howe. Each possesses a thick continental crust, ranging from 15 to 23 kilometers, or 9 to 14 miles, according to seismic data. This unusual thickness is explained by a tumultuous geological history, marked by tectonic ruptures and several episodes of uplift. The Campbell Plateau extends south of New Zealand, in waters buffeted by powerful currents. Long confused with oceanic crust, its foundation actually holds granitic rocks similar to those of emergent continents. Geophysical surveys have revealed a much greater thickness than initially estimated. This submerged mass reminds us that once, Zealandia formed a much larger continent before it slowly sank below sea level. Further east, the Chatham Rise features a distinct morphology. It extends under the sea, covered by sedimentary layers rich in marine fossils. Studies show that its sea level variations have influenced the local fauna and flora. In certain strata, tree pollens from tropical and subtropical regions reveal that a much warmer climate once prevailed over these now submerged lands. These discoveries fuel hypotheses about the region's plant evolution and illustrate the complexity of climate changes that shaped the ancient biodiversity of Zealandia. The third major part of Zealandia, the Lord Howe Rise, is located to the northwest. Unlike the Campbell and Chatham plateaus, this region bears the marks of an ancient, now extinct volcanism. Basalt flows and magmatic intrusions, buried under more recent sediments, are evidence of this past activity. Cores extracted during the Integrated Ocean Drilling Program have revealed ancient coral reefs, as well as fossil pollens dating from the Tertiary period, indicating that dense vegetation once thrived in a warmer and more humid climate. These clues strengthen the idea of an ancient emergence. The unusual thickness of Zealandia's crust, estimated between 15 and 23 kilometers or 9 to 14 miles, has intrigued researchers for decades. Using seismic reflection, a method that measures the return of waves sent into the subsurface, Geophysicists have shown that this crust, although submerged, reaches dimensions comparable to those of emerged continents. This discovery has overturned our view of the boundaries between land and oceans, revealing a transitional zone where older and lighter continental rocks sink under the sea. The scientific and economic implications of this distinction are significant. Among the tangible prospects related to Zealandia is the search for offshore hydrocarbons. Oil and gas are formed from organic matter buried in sedimentary basins, transformed by heat and pressure. The deep and ancient zones of Zealandia, rich in sediments, could host such deposits. To locate them, exploration companies analyze seismic profiles and conduct exploratory drilling. Despite the complexity and cost of these operations, the economic interest remains strong, but it is accompanied by debates on environmental issues. Another issue concerns phosphorate nodules, resulting from the accumulation of phosphate at the bottom of the seas. This mineral, essential for the production of fertilizers, attracts the attention of agricultural industries. These concretions form slowly in nutrient-rich waters. Their extraction could meet the growing demand for fertilizers, but it remains technically challenging and risky for marine ecosystems. Scientists therefore call for measured exploitation, favoring a sustainable approach. Finding a balance between economic development and the protection of the marine environment remains a top priority. For reconstructing the history of these plateaus, the Integrated Ocean Drilling Program plays an essential role. Scientists extract sediment cores by drilling the ocean floor at various depths. These samples, millions of years old, contain valuable clues: chemical composition, microorganisms, and especially fossilized pollens. Tertiary pollens reveal that thriving vegetation once covered some of Zealandia's emerged areas. Their diversity allows for the reconstruction of ancient climates, species distribution, and major tectonic upheavals. Each drilling is a direct plunge into the Earth's archives. The gradual submersion of Zealandia, once attached to the supercontinent Gondwana, profoundly altered the oceanic circulations of the southern hemisphere. As its lands sank under the waters, the regional geography transformed, opening new marine pathways and influencing currents on a planetary scale. This slow process, spanning tens of millions of years, has left precious traces for geoscientists. The progressive sinking of Zealandia has notably contributed to the widening and deepening of the Tasman Passage between Australia and New Zealand. The gradual opening of the Tasman Passage has been crucial in the establishment of the Antarctic circumpolar current. As this current gained strength, it began to encircle Antarctica on an almost circular path, gradually isolating the continent from the rest of the globe. By separating the cold polar waters from the warmer waters coming from subtropical areas, it established a highly active system of thermal and chemical exchanges in the Southern Ocean. This new dynamic facilitated the connection between the Pacific and Indian Oceans, durably influencing planetary climate balances. Before this reorganization, the waters surrounding Antarctica partially mixed with warmer ones coming from distant oceans. The opening of the Tasman Passage gradually altered these exchanges, creating a genuine marine corridor, facilitating the access of currents to the southern latitudes. The Antarctic circumpolar current, as it strengthened, functioned like an immense cooling system. By forming a barrier between polar and subtropical waters, it caused a progressive drop in surface temperatures, which favored the appearance and expansion of ice around the South Pole. This cooling did not happen overnight. It started during the Eocene, around 56 million years ago, and intensified in the Oligocene, around 34 million years ago. The global climate then shifted from a warm state to a more tempered configuration, marked by a progressive decrease in terrestrial and marine temperatures. The polar ice caps, previously almost absent, began to expand, forming the first great glaciations of Antarctica. These transformations have played a fundamental role in the architecture of the modern climate system. Among the major causes of planetary cooling, the modification of heat and salt exchanges between marine basins has played a key role. Once the Tasman Passage became wide and deep enough, ocean currents circulated more freely around Antarctica. This enhanced circulation, dominated by the Antarctic circumpolar current, accentuated the separation between warm and cold waters, ensuring better ventilation of intermediate and deep water masses. This mechanism gradually consolidated the transition to a cooler climate, accompanied by the expansion of the ice pack. In parallel, the ocean played a crucial role in planetary cooling by absorbing more carbon dioxide. This greenhouse gas can be captured by surface waters, especially when they are rich in nutrients. In the evolving Southern Ocean, upwellings brought up silica and other nutrients, stimulating the growth of phytoplankton. Through photosynthesis, phytoplankton absorbed a large amount of CO2, storing it in its organic matter and thus contributing to the decrease in global temperatures. Once dead, the plankton sank to the depths, carrying with it the carbon dioxide trapped in its organic matter. This transfer to the seabed reduced the amount of greenhouse gas in the atmosphere. In the long term, this mechanism contributed to maintaining a colder climate, complementing the insulating role of the Antarctic circumpolar current. This phenomenon, known as the biological carbon pump, drives CO2 from surface waters to deep sea sediments. The silica brought up by the upwellings favored the rapid growth of diatoms, microscopic algae with a silica shell. By multiplying, they enhanced the Southern Ocean's ability to absorb dissolved carbon dioxide. Once dead, they sink to the bottom, carrying carbon to the sediments. This interaction between silica, plankton, and marine chemistry not only intensified CO2 sequestration, but also allowed for the emergence of a very productive food chain in these cold waters. At the transition between the Tertiary and Quaternary periods, more than 2.5 million years ago, the Earth entered the Pleistocene, a time marked by alternating glacial and interglacial phases. Each cycle drastically transformed the landscapes, with immense ice caps periodically covering North America and Siberia. This phenomenon led to a drop in sea levels as water was trapped in the ice. It was in this context that Beringia appeared, a land bridge linking Asia and America, which formed around 2,600,000 years ago. To understand the formation of such a continental bridge, one must consider the Milankovitch cycles, named after Serbian scientist Milutin Milankovic. These cycles refer to the periodic variations in Earth's orbit, axis tilt, and its precession, which is the slow change of its orientation in space. When these parameters reduce summer insolation in the northern hemisphere, the ice expands significantly. Polar ice caps then retain enormous amounts of water as ice, causing a global drop in sea levels. During these episodes, polar regions become covered with thick ice sheets. At the peak of glacial phases, sea levels can drop by as much as 120 meters, 394 feet, below today's levels. This is known as eustatic lowering. In the northern Pacific, this drop exposes the Chukchi Plateau, a vast expanse connecting eastern Siberia to Alaska. Freed from the waters, this territory then forms an isthmus, several hundred kilometers, miles, wide. Beringia, named after the Bering Sea that covers it today. This phenomenon has repeated itself several times over climatic cycles, with each glaciation contributing to shaping the geography of this strategic region. The first significant emergence episodes of Beringia date back to the early Pleistocene. At that time, climatic fluctuations intensified, extending glacial environments over vast territories. Geological evidence like loess deposits, those wind-blown sediments, or certain fluvial formations indicate that Asia and America were sometimes connected. Beringia then became a natural bridge, facilitating the passage of animal species, and later, human groups. These migrations into higher latitudes marked a crucial turning point in the history of life and human evolution. Milankovitch cycles alter Earth's solar heat distribution. When the northern hemisphere receives less heat in summer, glaciers expand more easily. Ice volume increases, leading to another drop in sea levels. Millennia later, when astronomical parameters reverse, the ice melts and the sea rises, submerging Beringia once again, until the next glacial cycle. This rhythmic ebb and flow dictates the formation and disappearance of continental bridges, conditioning animal and human migrations through the ages. In emergent Beringia, the climate is cold but dry, as moisture is trapped in the ice caps. Drying winds sweep across vegetation, dominated by frost-resistant grasses like grasses and sagebrush. This steppe tundra environment hosts large mammals like the woolly mammoth, bison, and horse, which migrate in search of seasonal pastures. Their movements ensure genetic mixing between continents, making Beringia a true biological corridor. This landscape is a testament to a dynamic fauna, perfectly adapted to extreme conditions. Scientists agree that the gradual formation of these land corridors facilitated the migration of human populations from Asia to America. Although the exact date is still debated, archaeological and genetic evidence suggests that the first Homo sapiens followed herds by crossing Beringia. This territory was not just a simple passage, it was a true ecosystem, rich in game and edible plants. The hunter-gatherers adapted to it, developing survival strategies in a harsh but generous environment. This migration marks a major turning point in human history. Indeed, as the ice caps recede, ocean waters rise and submerge Beringia. The Bering Strait then reappears, interrupting land exchanges between Asia and America. This cycle repeated itself several times during the Pleistocene. In each glacial period, the bridge formed again, facilitating migrations before disappearing during climate warmings. Thus, Beringia embodies a key player in climatic history, illustrating how glaciations shape global geography. The Beringian Plain, between Northeast Asia and Northwest America, was shaped under the influence of cold climates and deeply frozen soils. When sea levels were much lower, it formed a natural bridge between two continents, facilitating animal and human migrations. To understand its organization, one must examine the tundra steppe, loess deposits, freeze-related formations like pingos, and the polygonal soils, as well as the river networks that cross it. Finally, the Brooks and Verkhoyansk ranges in Alaska and Siberia block Atlantic influences, establishing a continental climate with harsh winters and brief summers. The tundra steppe of the Beringian Plain is a hybrid ecosystem combining characteristics of the treeless tundra, dominated by mosses, lichens, and dwarf plants, and the steppe, covered with drought-resistant grasses. This unique landscape results from a cold and dry climate, punctuated by brief, milder seasons, where low vegetation grows rapidly. This sparse vegetation favored the movement of large herds of herbivores in search of food, while providing predators with a clear territory for hunting. Unlike the dense forests of the south, This open plain concentrated biodiversity, adapted to the rigors of freezing and seasonal aridity. The loess, deposits of fine dust transported by the wind, play a key role in understanding the Beringian plain. Formed during glacial periods, they originate from the erosion of rocks by glaciers in ranges like Brooks or the Siberian reliefs. Powerful winds then disperse these particles over vast areas. Once deposited, loess forms a fertile soil, but particularly vulnerable to erosion. In a cold climate, this layer is often frozen, making it temporarily stable. But during a warming, even brief thawing of the superficial soil can cause rapid gullying, exposing these fragile sediments. Among the typical phenomena of the Beringian plain, pingos stand out with their dome or conical shape. These small hills form when groundwater, trapped under permafrost, the layer of soil frozen permanently, freezes in turn. As it solidifies, it increases in volume and lifts the surface of the ground, forming a mound whose core is made of ice. Some pingos can measure several dozen meters, or about 328 feet, high and exceed 100 meters, or 328 feet, in diameter. Besides their spectacular appearance, they provide valuable information on the behavior of frozen soil, variations in water tables, and climatic evolutions in cold regions. On the surface of the Beringian plain, frozen polygonal soils are often hexagonal or pentagonal. These geometric patterns result from repeated cycles of freezing and thawing, which crack the soil into blocks separated by crevices. In winter, water infiltrated in these crevices freezes and expands, widening the fractures. During the brief summer periods, only the surface layer partially thaws, without completely closing the crevices, maintaining and accentuating this pattern. On the ground, these shapes give the landscape an almost artificial appearance, as if they had been hand-drawn. Direct witnesses of the polar climate's influence, polygonal soils reflect the combination of intense cold and weak seasonal warming. In the Beringian plain, river networks played a key role. When the Bering Sea was reduced, many rivers formed braided channels, which means branches that separated and rejoined in a complex network. Fed by the seasonal melting of snow and northern glaciers, these waterways traversed an overall dry environment, providing a vital resource for the wildlife and the rare human groups present. With the gradual rise of the sea level, these rivers saw their course shorten, eventually flowing into the Bering Sea, now vast enough to permanently separate Asia from America. The Beringian landscape was also shaped by the mountain ranges that bordered it. North of Alaska, the Brooks Range, with its peaks reaching 2,000 meters or 6,562 feet, formed a barrier limiting the arrival of moisture from the central Arctic. On the other side, in eastern Siberia, the Verkhoyansk Range, peaking at over 2,500 meters or 8,202 feet, played a similar role against the humid flows from the Atlantic. Enclosed between these two chains, the Beringian plain remained cut off from temperate and oceanic influences, accentuating the harshness and dryness of its continental climate. The influence of the mountains on the local climate is manifested by intense polar winters, with temperatures sometimes dropping below 30° or 20°, and very short summers, limited to a few weeks of warmth. The rare air currents able to cross these reliefs only pick up moisture if the Bering Sea is not completely frozen. However, during glacial periods, the ice extended much further south, slowing evaporation and significantly reducing precipitation. This moisture deficit, combined with the extreme cold, explains the absence of forests and the dominance of low, sparse vegetation, perfectly adapted to this harsh environment. Wind erosion, amplified by strong winds and the rarity of precipitation, greatly contributed to the formation of loess deposits over vast areas. These glacial particles, transported over long distances, settle where the wind weakens, particularly in sheltered valleys. Over time, they form thick layers. Subjected to freeze-thaw cycles, these strata crack, reorganize, or compact, actively participating in the evolution of soils in this extreme environment. At the heart of the prehistoric cold, the Mammoth Steppe extended like a vast ocean of grasses. Its vegetation grouped robust species such as Poaceae, Artemisia, and Dryas, capable of withstanding temperatures often below 10 degrees C or 50 degrees Celsius. These plants formed a productive community essential to the survival of megafauna. The Poaceae, a large family of grasses and cereals, constituted the base of this flora. Their rapid growth allowed them to take advantage of the slightest thaw to produce young shoots. Their biomass fed large herbivores, while their deep roots stabilized the frozen soils, reinforcing the resilience of this extreme ecosystem. Artemisia, or mugwort, groups aromatic plants adapted to dry soils. Their deep roots allowed them to draw water despite the frost, while their astringent leaves protected them from diseases and insects. Their diversity enriched the diet of the fauna, strengthening the ecosystem's resilience to harsh seasons. The creeping bushes of Dryas better captured heat and mitigated the effect of the winds. Their leaves retain moisture and protect the soil from drying out. By stabilizing the substrate, they limited erosion in this frozen environment. In spring, their early flowers served as a refuge for insects and contributed to the ecological balance of the steppe. The interaction between plants and large herbivores explained the remarkable productivity of the Mammoth Steppe. The grassy mass fed large animals like the woolly mammoth, whose movements favored vegetable regeneration. Their heavy hooves aerated the soil, and grazing stimulated regrowth. This dynamic created a virtuous cycle. The more fauna thrived, the more flora developed, ensuring the ecosystem's balance. In sheltered valleys, the Dahurian larch formed small groves away from the winds. Its deciduous needles limited evaporation and prevented snow accumulation. The valleys provided accessible groundwater, allowing these trees to root sustainably. Although rare, these wooded islands enriched biodiversity and served as a refuge for fauna. The Dahurian larch, Larix dahurica, exhibited remarkable adaptation. It shed its needles in the fall, reducing evaporation and limiting damage from the cold. Its deep roots avoided surface freezing, and as soon as the good weather returned, it quickly leafed out, making the most of the sunlight. Isolated yet resilient, these trees supported biodiversity, providing shelter and resources to numerous species. Nearby, in poorly drained areas, stagnant water formed acidic bogs dominated by sphagnum mosses. These plants, capable of retaining large amounts of water, gave the soil a spongy appearance. The lack of oxygen slowed decomposition, accumulating a thick layer of peat. Only highly specialized plants could survive there, contributing to water regulation in this extreme environment. In these peaty marshes, the leatherleaf shrubs found their place. The acidic soil hindered most plants, but they survived thanks to symbioses with microorganisms that facilitated the absorption of nutrients. Their delicate bell-shaped flowers appeared during the rare mild periods. Alongside the sphagnum mosses, these shrubs helped preserve the ecological richness of these wetland areas. These acidic bogs functioned like real sponges. They captured water from the melting snow in the spring, then slowly released it during dry periods. This natural storage regulated the water balance of the entire ecosystem, providing a reliable water source for the fauna and flora. These wet basins thus became vital meeting points in the heart of the mammoth steppe. Far from being monotonous, these varied environments hosted abundant life. Aquatic insects, birds, small mammals all benefited from these wet zones, where the surrounding grasses thrived thanks to the moisture. Even large herbivores would visit to drink or cool off. Thus, each peaty corner, even discrete, contributed to the richness and balance of this impressive ecosystem. Ultimately, the paleoflora of the mammoth steppe combined Poaceae, Artemisia, and Dryas on the open lands, while Larix dahurica grew in some sheltered valleys, and sphagnum and leatherleaves occupied the bogs. This plant diversity painted a landscape that was both rich and austere. Fossil pollen proves the remarkable adaptability of these plants, capable of blooming despite the cold, thus supporting a large number of fauna. By reconstructing this ancient flora, researchers discover fossil leaves, petrified wood, and pollen grains. These remains reveal how each species occupied a well-defined niche. Poaceae dominated dry soils, sphagnum, the water-saturated environments. Fascinatingly, pollinating and saprophytic insects already accompanied these plants, testifying to the complex interactions that maintain the balance of this extraordinary ecosystem. Understanding this extinct flora allows us to appreciate the complexity of ecological interactions in extreme climates. Behind the apparent austerity of the steppes, intense life unfolded, driven by astonishing adaptation strategies. Today, studying the paleoflora of the mammoth steppe sheds light on the remarkable ability of the biosphere to withstand climatic upheavals. It also serves as a reminder that no species, even the most discrete, is useless in the balance of life. It was in the heart of Beringia, this vast region that once linked Alaska to Siberia, that an exceptional megafauna evolved during the glacial stages. In this hostile environment, where temperatures plunged well below zero, imposing herbivores roamed an arid steppe, yet rich in grasses. Among them were the woolly mammoth, the steppe bison, and the Beringian horse, respectively Mammuthus primigenius, Bison priscus, and Equus lambae in Latin. Together, they formed the base of a food chain populated by formidable predators and watchful scavengers. The woolly mammoth was one of the most iconic herbivores. Its dense fur and long curved tusks allowed it to survive in the freezing cold. It used them to clear the snow and reach the buried vegetation. In tight-knit family groups, they migrated across the steppes in search of food. Their diet consisted of hardy grasses and small plants that they unearthed by digging through the snow. These constant movements allowed the species to thrive for millennia, despite an extremely hostile environment. Another iconic giant, the steppe bison, survived the extreme cold thanks to a thick coat and an insulating layer of fat. Weighing more than 600 kilograms or 1,223 pounds, it fed on dry grasses and tough plants. Although imposing and equipped with horns, it mostly relied on the protection of the herd. By migrating far from heavily snow-covered areas, these groups accessed more food and avoided predators. By moving, they also helped disperse seeds in their environment. Less imposing, but just as important, the Beringian horse completed this trio of tundra steppe herbivores. Smaller than modern horses, it was remarkably hardy. Thanks to its sturdy hooves, it dug through the snow to reach the few buried chutes. To protect itself from predators, it lived in close-knit herds, benefiting from collective vigilance. Its resilience allowed it extensive seasonal migrations in search of new pastures in the snowy vastness of Beringia. In this fragile balance, several predators dominated the food chain. The cave lion, or Panthera spelaea, roamed the plains in search of young mammoths or weakened bison. Agile and powerful, it remained formidable even in environments less favorable to ambush. Fossils show that it could target more massive prey, likely due to opportunistic techniques or occasional cooperation. This predation helped regulate herbivore populations. Another iconic carnivore, the dire wolf, or Canis dirus, lived in packs much larger than those of today's wolves. More massive, it had a jaw powerful enough to crush bones. It primarily hunted isolated horses or weakened bison, leveraging an effective collective strategy to feed the entire group. Fossils indicate that it roamed vast territories, following its prey over hundreds of kilometers or miles during winter. Alongside the canids, a legendary feline caught everyone's attention: the saber-toothed tiger, or the Siberian Smilodon populator. With its long, dagger-shaped canines, it could fell large herbivores with a single strike. Although native to temperate regions, this northern Smilodon adapted to the cold steppes, benefiting from compact herds for regular feeding. Its effective hunting method contributed to ecological balance by limiting the overpopulation of large herbivores. Around these great predators, some smaller animals adopted a scavenger strategy, feeding on leftovers from the hunters. The Arctic fox, in particular, played a crucial role. Compact and covered in thick white fur, it withstood extreme cold down to 20 Celsius or 4 degrees. With an exceptional sense of smell, it quickly located abandoned carcasses. This behavior helped limit waste and contributed to efficient natural recycling in these harsh environments. Finally, the majestic cinereous vultures completed this circle of life, soaring above the icy plains. Their large wingspan allowed them to cover great distances to spot carcasses. With a very resilient digestive system, they could consume decaying flesh, ensuring a natural cleanup of the landscape. Their presence, discreet but essential, limited the spread of diseases. Thus, each species contributed to the balance of this glacial ecosystem, where every role fit perfectly to sustain life. Yet, over the millennia, climatic variations upset this balance. The advance or retreat of the ice altered the pastures, forcing mammoths, bison, and horses to change routes. Predators like the Smilodon or the dire wolf had to adapt, sometimes at the cost of a decline. Despite this, during the Great Glacial periods, Beringia remained a vital refuge, where this remarkable fauna could survive and leave a lasting mark on natural history. About 24,000 years ago, in the boreal expanses of Northeast Asia, small groups of Homo sapiens crossed a now-disappeared natural boundary, reaching a territory that would become a key migratory bridge. We are talking about the Yukagir culture, a little-known people but crucial for understanding human settlement during the Paleolithic in these regions. This episode marks the arrival of populations capable of surviving a harsh climate, where winter stretched over almost the entire year. The term Yukagir refers less to a specific people than to a particular way of life and skill set. This culture is distinguished by its mastery of knapped stone tools, essential for the survival of nomadic hunter-gatherers. Flint, easily accessible, was shaped to create sharp blades, ideal for cutting meat or working with skins. Among the techniques used, pressure flaking allowed the removal of thin flakes using a wooden or bone tool to obtain very precise edges. These blades were used for various tasks, preparing skins, cutting meat, and shaping objects. Through this method, the Yukagirs conserved their raw materials while making efficient tools that were easy to carry and quick to replace when worn out. Besides flint, the Yukagirs also used bone and mammoth ivory, abundant in the frozen steppes. Ivory was used to craft hunting tips that were both lightweight and strong, ideal for capturing bison and reindeer. As for bone, it was used to make spears, needles, or smoothers, essential for sewing and treating skins. To survive in these hostile territories, they designed semi-subterranean shelters. By digging into the ground, they created an insulating base, reinforced by a framework of mammoth bones on which skins were stretched. The whole was covered with clumps of earth and peat, forming an effective barrier against the cold. This type of dwelling offered a relatively comfortable shelter, protected from the wind, allowing for some warmth retention during the long winters. Although modest, these shelters offered a vital refuge during the long winters. Inside, one or more fire areas served as sources of heat, light, and cooking. Dried bones or driftwood gathered near the shores, or the rare groves were burned. The hearths allowed for the cooking of mammoth, horse, or smaller game meat, ensuring a diet rich in proteins and fats. Life was organized around collective tasks, preparing meals, maintaining tools, or sharing stories. Old tips were resharpened using small strikers, while skins used as clothing or blankets required regular care. In this extreme climate, cooperation was indispensable. Everyone had a role to ensure survival. Children from a young age learned to track animals, recognize frozen grounds, and understand their environment. According to remains found at several Siberian sites, the Yukagir culture is distinguished by a great capacity for adaptation, which allowed them to expand into some of the most hostile environments. These human groups did not hesitate to travel long distances to follow migratory herds. When they spotted a source of flint or usable stone, they settled temporarily to replenish their stock of tools. This mobility allowed them to make the most of resources without overexploiting local game. Hunting remained their primary activity. To capture a mammoth or bison, they employed clever techniques, driving the animals toward a ravine or a marsh, and then finishing them with flint or ivory tips. The carcasses were then meticulously butchered. The distribution of remains on the sites shows that nothing was wasted. Meat, fat, long bones, tendons, everything was recovered. This organization demonstrates a mastered know-how, essential for their survival. Beyond survival, the Yukagir culture seemed to carry its own beliefs and traditions, passed down over generations around the firesides. Although direct evidence is scarce, some bone or ivory objects featured geometric incisions, suggesting rituals or artistic sensitivity. Clues suggest that these groups already honored their dead through simple rites, even though clearly identified burials remain rare. Over time, their descendants continued their migration eastward, crossing the Bering land bridge to reach North America. The Yukagir culture thus embodies the remarkable adaptability of humans to the extreme constraints of a glacial environment. Glacial refuges refer to areas where certain species were able to survive despite the intense cold of glacial periods. During the Pleistocene, these sanctuaries allowed groups threatened by the advance of massive ice sheets to persist. Their impact is still found today in the DNA of many populations, including the first inhabitants of the Americas. In this context, the Beringian standstill model suggests that the ancestors of the Native Americans remained isolated for about 5,000 years around the Yukon Basin, between Siberia and Alaska. This region, spared by the glaciers, formed a rare refuge, while gigantic ice masses blocked any progress eastward or southward. Despite limited resources, these human groups managed to survive, maintaining a stable population over millennia while awaiting the opening of new passages. The prolonged isolation in Beringia encouraged the emergence of specific genetic mutations observable in maternal mitochondrial DNA. Among them are haplogroups A2 and B2, true imprints of the past. A haplogroup denotes a genetic lineage transmitted generation after generation, identified by specific mutations. A2 and B2 thus encompass characteristic variations unique to the populations that lived in this glacial refuge. These markers today make it possible to trace the origin and dispersal of the first Native Americans. When the climate warmed and the glaciers retreated, these human groups migrated southward. The opening of new land corridors facilitated their expansion across the continent. This foundational movement contributed to the diversity of indigenous peoples in North and South America, laying the groundwork for the first sustainable societies in the New World. The early Holocene marked the abrupt end of the Beringian episode. With the rapid melting of ice, sea levels rose significantly. Around 11,700 years before our era, or approximately 11,700 years ago, vast territories once emerged were submerged, engulfing Beringia. This sea level rise permanently severed the land connection between Eurasia and America, closing this migration corridor. The groups settled on the American continent remained isolated, while their Asian counterparts could no longer cross the ocean. This climatic upheaval transformed coasts and erased the ancient tundra steppe landscapes, once trodden by mammoths and hunter-gatherers. Today, only a deep strait remains, separating two continents. This geographic rupture played a major role in the cultural and genetic history of the peoples of America, setting them on an autonomous evolutionary path. The impact of the Beringian standstill is still observable today through genetic analyses. By comparing DNA extracted from ancient human remains or current populations, researchers have identified haplogroups A2 and B2 in many Native Americans. These markers confirm that these groups were isolated for millennia before dispersing when the climate became more favorable. Thanks to modern technologies, such as high-throughput sequencing, it's possible to detect subtle variations in DNA. These reveal a genetic drift, typical of groups that remained confined. In the Beringian case, this isolation acted as a filter. Indeed, only a part of the initial diversity was maintained. This bottleneck left specific genetic signatures still visible in the maternal DNA of indigenous peoples. The study of glacial refugia is a cornerstone of paleoanthropology, as it shows how climate and geography have shaped human migrations. The history of Beringia, until its disappearance beneath the sea helps understand the differences between indigenous peoples of America and their connections with certain populations in Northeast Asia. The Holocene warming, beginning approximately 11,700 years ago, dramatically altered the climate inherited from the last glaciation. At that time, massive ice sheets, known as ice caps, still covered a large part of the northern hemisphere, such as the Laurentide ice sheet in North America or the Siberian ice sheet in Eurasia. These ice masses, sometimes several kilometers or miles thick, began to melt rapidly due to rising temperatures, releasing enormous amounts of fresh water into the oceans and profoundly altering the global climate balance. The sea level rise, about 60 meters or 197 feet in 2,000 years, deeply reshaped the northern landscapes. The Bering Land Bridge, once a connection between Asia and America, was submerged, giving way to the Bering Strait we know today. This massive melting of the Laurentide and Siberian ice sheets was linked to a progressive warming of the climate, driven by Milankovitch cycles. Adding to this was a natural increase in atmospheric carbon dioxide, enhancing the greenhouse effect. Together, these phenomena ended the last glacial period, accelerating ice melt and permanently transforming global geography. The Bering Land Bridge gradually disappeared beneath the waters as the glaciers melted. Before that, it was a vast landscape inhabited by species adapted to a cold, dry climate with low precipitation. As glaciers retreated, coastal erosion increased and advancing oceans fragmented ecosystems. This fragmentation greatly affected biodiversity, reducing vital areas for many species, especially those dependent on the tundra for food and reproduction. The ancient ecological corridors disappeared, pushing some animal populations to migrate or go extinct. Among the species affected by these upheavals, the Beringian horse holds a particular place. Once abundant in Eurasia and America, this herbivore was well adapted to the cold, dry conditions, with a dense coat and robust limbs, ideal for moving through steppe vegetation. But the rising seas and the disappearance of open spaces reduced its grazing areas. As the climate became more humid in some regions, the vegetation thickened, making it more challenging for large herbivores like it to feed. These changes severely compromised its survival, contributing to its gradual decline at the end of the last glacial period. The decline of the Beringian horse accelerated due to the combined effects of climate change, predation by large carnivores, and increasing pressure from human groups. While ice sheets melted, other major transformations affected the planet. The gradual disappearance of the Bering Land Bridge, covered by water, remains one of the most striking events of the early Holocene. Lowlands were submerged, leaving only a few isolated heights, forming an archipelago of small, scattered islands. The transformation of habitats drastically limited the movements and seasonal migrations of animal species, pushing some to adapt and others to disappear. Already weakened by the scarcity of resources, the Beringian horse did not survive. It left behind fossils, last witnesses of its presence in North America. This extinction is part of a series of disappearances that marked the end of the Pleistocene and the beginning of the Holocene. With the rapid warming of the climate, many large-sized species, inflexible in the face of change, went extinct. The fate of the Beringian horse reminds us of how environmental upheavals can weaken ecosystems and lead to the collapse of species that lack sufficient plasticity to adapt in time. Thanks to advances in paleoclimatology and paleontology, scientists are now able to trace the evolution of sea levels and wildlife movements. By analyzing sediments, fossil pollens, or bones found in ancient tundra areas, they have better understood how these vast landscapes gradually vanished due to rising oceans. The Bering Strait, which emerged from this submersion, now separates Russia from Alaska by nearly 90 kilometers or 56 miles. It embodies the profound transformations caused by post-glacial warming. The marine currents running through it today play an important role in the regional climatic balance by regulating the circulation of heat and providing essential nutrients to Arctic marine ecosystems. Doggerland refers to an ancient plain now submerged, which once connected Great Britain to continental Europe. During the glacial periods of the Pleistocene, the level of the North Sea was much lower because much of the water was trapped in ice caps. This vast territory formed a gently sloping plateau composed of plains and valleys. When glaciers expanded, the sea receded, revealing the shallow plain. Great Britain was then connected to Jutland, the Danish peninsula, as well as to the lands that now border the Netherlands and Germany, such as Friesland. This terrestrial continuity allowed animal and human populations to move freely across a vast emerged space. The landscape of Doggerland was characterized by gentle relief, with softly marked hills and discrete depressions. As far as the eye could see, these undulations were crossed by rivers, which played an essential role in shaping the terrain. Valleys resulting from large rivers like the Solent Thames, the Elbe, or the Vecht created fertile corridors ideal for wildlife. During glacial periods, a large portion of freshwater was trapped in ice. Precipitations then flowed through a network of rivers, which, over the millennia, sculpted the surface. The Solent and Thames rivers converged toward a basin, now submerged under the North Sea, while the Elbe extended its bed well beyond the current coasts. These river systems shaped a vibrant landscape, molded by water, and provided a favorable setting for the settlement of both human and animal species. The Vecht River, now located in the Netherlands, was once part of the vast hydrographic network of Doggerland. During the Pleistocene, it traversed a vast plain, nourishing wetland areas rich in biodiversity. With climatic variations, its valleys widened or became obstructed, creating a succession of habitats whose traces are found in the current sediments of the North Sea. In addition to river valleys, Doggerland also hosted continental dunes. These formed when strong winds in cold regions lifted the sands revealed by the retreat of the sea or the melting ice. Gradually, these dunes took shape as sandy hills, transforming the landscape. They sometimes served as natural barriers, slowing down floods caused by river surges or temporary rises in sea level. In some areas, the action of glaciers located further north gave rise to proglacial lakes, bodies of freshwater held back by ice or frozen sediments. These lakes often formed in low-lying areas where water stagnated, creating isolated environments favorable to particular aquatic flora and fauna adapted to the cold. These water bodies played an important role in the local hydrological balance. Their appearance depended on both the configuration of glaciers and the surrounding relief. In some places, large moraines, accumulations of debris left by glaciers, blocked the water flow, thus forming temporary basins. Although they disappeared with warming, these lakes left deposits rich in clays and microfossils, testifying to their past biodiversity. During glacial peaks, Doggerland was not a mere frozen plain. It was a complex landscape, shaped by freezing, thawing, winds, and waterways. The climatic variations of the Pleistocene slowly sculpted this territory, transforming it continuously. Continental dunes, river valleys, and proglacial lakes reflected both the apparent stability and vulnerability of this changing world. The dunes also bear witness to active erosion. During dry phases, vegetation became sparse, allowing the wind to carry sand over long distances. These accumulations formed moving, sometimes unstable, reliefs. The highest dunes could slow the passage of migrating animals, while neighboring wetlands offered shelter and resources. This precarious balance between mineral elements, climate, and biodiversity made Doggerland both a hostile and welcoming space, where every form of life had to adapt to the constant changes in the landscape. During the pre-bulling period, this herbaceous tundra landscape basked in a cold climate, with summers barely mild and winters harsh, well below 0 Celsius. In this austere setting, only the most resilient plants survived. 2 species dominated this vegetation, Salix polaris and Betula nana. The first, a dwarf willow, measuring only a few centimeters or inches, grew in poor soils despite the icy wind. The second, the dwarf birch, efficiently exploited moisture with its extensive roots and low silhouette that defied frost. Together, these 2 plants created a thin layer of greenery over a landscape swept by cold, bringing a touch of life to this mineral and silent space. Sediment cores, extracted from beneath the North Sea, have revealed fossilized pollens tracing the plant history of Doggerland. Among them, grains of Pinus sylvestris suggest short warming episodes, enough to allow its germination. According to paleontologists, these brief warm spells temporarily altered the vegetation by introducing pioneer trees. Then, the climate turned harsh again, erasing these traces of greenery, like a fragile breath in a landscape often frozen by the cold. Despite some seasonal nuances, Doggerland remained dominated by the tundra, low vegetation rooted in shallow soils, frozen much of the year. It primarily consisted of grasses, sedges, and creeping plants, pressed to the ground to withstand the winds. In poorly drained wetlands, mosses and liverworts, bryophytes fond of cold, thrived. Their presence, typical of water-saturated environments, made them valuable indicators of a harsh glacial climate. Sometimes covered in ice crystals, mosses and liverworts played a vital role. They trapped moisture, shielded the soil from the wind, and promoted the formation of a thin layer of humus. This layer allowed, during milder periods, the germination of more demanding plants like certain dwarf shrubs. By retaining water, these bryophytes also created small oases for microorganisms. Their presence ensured a fragile but essential balance, reinforcing the resilience of Doggerland's tundra. The analysis of fossilized pollens has shed light on how important this vegetation was for fauna. Small mammals fed on the buds, while rodents sheltered under the creeping branches. For large herbivores, these grasses offered, despite the harsh climate, minimal resources during the fair season. Their low stems also helped stabilize the soil, limiting erosion. Over time, cycles of warming and cooling shaped, in successive waves, the living landscape of Doggerland. The fragile balance of the tundra depended on its ability to develop on periodically frozen soil known as permafrost, present when freezing persists for several years in deep layers. During the pre-bulling interval, this permafrost was likely discontinuous in Doggerland, influenced by the proximity of the Atlantic and a more temperate latitude. This instability allowed plants, like Scots pines and dwarf birches, to spread locally before retreating with new temperature drops. As long as light and moisture sufficed, plant life always found a way to persist. Let us go back to a time when the North Sea did not yet exist. In its place stretched Doggerland, a vast, fertile territory populated by wild animals. In this section, let's explore the richness of its fauna. First, the large herbivores, then the predators, before diving into the marshes teeming with birds. Among the first inhabitants were reindeer. Their thick fur and wide hooves made them perfectly adapted to wetlands, where they fed on mosses and lichens while encouraging the landscape's regeneration. In these plains lived elk as well, even more massive than the reindeer. Their powerful limbs and broad hooves allowed them to progress through the marshes in search of bark and young shoots. By consuming the dense vegetation, they contributed to the ecological balance. Solitary most of the time, they gathered for sonorous displays during the mating season. But the most impressive was undoubtedly the giant deer, Megaloceros giganteus. Its antlers, immense and branched, sometimes exceeded 3 meters or 10 feet. During displays, the males clashed in spectacular duels to woo the females. This majestic giant, a symbol of Doggerland, remains an enigma for researchers. Its extinction remains unexplained. Doggerland could never have supported so many herbivores without the presence of formidable predators. Among them, Canis lupus, the wolf, played a fundamental role. Living in packs, they relentlessly pursued weakened reindeer or elk. Together, the wolves isolated their target and brought it down, helping to maintain a natural balance. Their vast territory drove them to roam marshes, forests, and plains, influencing prey distribution. Alongside them, the brown bear, Ursus arctos, roamed the banks and undergrowth. Less dependent on hunting, it alternated berries, roots, fish, and carrion. Moving through environments, it scattered seeds and shaped the landscape. Discreet but essential, it added a touch of harmony to this well-tuned ecosystem. Less imposing than the bear or the wolf, the wildcat, Felis sylvestris, prowled silently in the thickets of Doggerland. A discreet and solitary predator, it stalked rodents and small birds under the cover of night, spotting its prey with remarkable precision. This shadowy hunter played a key role. It kept the proliferation of small animals in check, which, if overabundant, could have destabilized the meadows and marshes. Adaptable and stealthy, it navigated the seasons with agility, maintaining balance quietly, but with constant efficiency in this ever-evolving world. In the wetlands of Doggerland, avian life was in full swing. Large flocks of geese chattered at stopovers, searching the banks to find seeds and vegetation. More graceful, the swans dipped their necks into the mud to extract roots and stalks, moving in pairs in a silent ballet. The grebes, agile little divers, built their floating nests sheltered among the reeds between two dives in search of insects or fish. Together, these birds punctuated the marshes with their calls and flights, while spreading seeds and plant fragments as they moved. Ultimately, the coexistence of ruminants, predators, and aquatic birds composed an ecosystem of rare complexity. Each species had its place and role, contributing to a vital balance. At the dawn of the Mesolithic, between 11,000 and 8,200 years ago, a new chapter opens in human history, at the heart of the lands that today correspond to the east of England. It is the Middle Stone Age. In this transitional time, humans lived by hunting and gathering, establishing seasonal camps deeply connected to nature. The rivers, winding through the plains, offered them water, food, and direction, while the sparse forests and wetlands became subsistence grounds. Mobility was essential. Groups settled on heights near waterways, safe from floods. Their shelters, made of stretched hides or branches, were simple, dismantleable, and easy to transport. As soon as game became scarce or resources were exhausted, they packed up and moved on. Thus, these Mesolithic communities adapted their way of life to the very breadth of the landscape. Here, we will explore the technical mastery of Mesolithic hunter-gatherers, illustrated by the making of flint microliths. These small, sharp tools, produced from local flint, were mounted on shafts using resin or tendons to form arrows, blades, or harpoons. Their compact format facilitated transport and replacement, revealing a modular and ingenious approach. This strategy reflected the importance of lightness and practicality in the nomadic life of these groups, always in search of adaptability. Large herbivores like deer or roe deer were at the heart of the subsistence strategy. Their meat provided food, their skins provided clothing, and their bones served as tools. These collective hunts reinforced group cohesion. In parallel, hares and birds rounded out the diet. Fine observation of the seasons guided their movements, as climatic and vegetative variations influenced animal migrations, forcing groups to adjust their itinerancy with precision. Fishing was a strategic activity for Mesolithic societies. The winding rivers, with their calm and shallow areas, attracted migratory salmon and eels. Salmon were fished during their seasonal upstream journeys, while eel, available year-round, supplemented the diet. Techniques varied: wooden traps, bone spears, or hooks. Knowledge passed down orally helped identify the right places and times. These outings, sometimes collective, reinforced group solidarity around shared knowledge. This highlights the social and cultural dimensions of Mesolithic campsites. The campfire became a place of learning, storytelling, strategy, and celebration. These gatherings reinforced group bonds and allowed the transmission of knowledge and traditions to the younger ones. In this communal atmosphere, a modest yet significant form of art emerged in the form of bone engravings, showing that these societies were not merely surviving. They were thinking, narrating, and creating. The deer, emblematic of these landscapes, held a central place in Mesolithic material culture. Its meat nourished, its skins protected, its bones became tools like spatulas, points, or knife handles. Some fragments reveal engraved motifs, geometric figures, stylized animals, or enigmatic signs. What we call mobile art, portable and discrete, carries traces of a rich collective imagination, both aesthetic and spiritual. Among the most striking vestiges of this symbolic dimension are modest sandy mounds, probably used as graves. Although the evidence remains fragmentary, it is presumed that these mounds housed some deceased, perhaps the most respected. Burials, sometimes accompanied by objects like flint points, suggest a desire to honor the dead and mark a transition. These gestures bear witness to structured thought around the cycle of life and memory, laying the foundations of a spirituality still unknown, but already well present. In this context, honoring the dead extended attachment to the territory. The mounds may have signaled that an ancestor rested there, becoming lasting markers in changing landscapes. Placed on heights, they perhaps served as gathering points between groups, fostering meetings and seasonal rituals. The engravings made on deer bones testify to a strong symbolic link between human groups and the fauna they hunted. More than just a food resource, these animals represented mythical figures with whom communities established a ritual dialogue. Archaeological discoveries confirm the regularity of hunting, but also reveal that it was part of a worldview imbued with respect and spirituality. This passage emphasizes the crucial role of cooperation and transmission in Mesolithic societies. Each member contributed according to their skills, and children learned through observation and imitation. The elders, keepers of the collective memory, played a key role in training the younger ones. This intergenerational weaving not only allowed for the effective distribution of tasks, but also the preservation of knowledge, essential for survival in a demanding nomadic lifestyle. These gestures revealed a desire to leave a lasting mark on the environment while promoting cultural exchanges between communities, proof that social and spiritual life far exceeded the mere imperatives of survival. We conclude with sensitivity about the symbolic value of archaeological remains. Even if minimal, these traces allow us to sketch the lives of Mesolithic populations, profoundly linked to their environment. In harmony with the nurturing rivers, these people built traditions, some of which have endured through the ages. The analysis of tools, burials, and art shows that these societies were far more elaborate than their apparent simplicity suggested. Despite a portion of their history being submerged, their legacy remains readable and deeply inspiring, highlighting humanity's ability to innovate, adapt, and leave lasting marks on landscapes and memories. Let's begin with the Storegga catastrophe, a massive underwater landslide that occurred off the coast of Norway. This phenomenon triggered a tsunami over 15 meters or 49 feet high, capable of submerging entire regions. It is considered one of the largest events of its kind ever identified. This natural disaster not only reshaped certain coastlines, but also remained engraved in the sediments of the North Sea, thus offering scientists a valuable marker of the region's environmental history. At that time, the gradual retreat of ice caps was relieving the Earth's crust of their weight, destabilizing the sedimentary layers of the continental shelf. Due to melting and rising sea levels, waterlogged sediments became vulnerable. The slightest slope rupture could then trigger a sudden collapse. These regions were already experiencing isostatic adjustments, accentuating this invisible fragility. Suddenly, thousands of cubic kilometers or miles of material tilted, generating a titanic marine wave. Just like when a massive object drops into the water, the sea reacts by producing a wave that, although losing height along the way, retained its destructive force when reaching the coasts. The landslide area would have covered several hundred kilometers or miles, well beyond the current North Sea. In the Mesolithic era, the low plains of Doggerland, rich in marshes and inhabited by hunter-gatherers, formed a fertile territory between Great Britain and Europe. When the Storegga tsunami struck, it brutally swept away the most exposed areas. The wave carried away vegetation, deposits, and human installations, forcing wildlife and inhabitants to hastily flee to higher ground. In a few hours, this fragile balance was shattered, marking a dramatic turning point for those living there. Evidence of this catastrophe is buried in marine sediments. Extracted core samples reveal layers of clayey turbidites, born from the suspension of sediments by the wave. These dark layers, rich in clays and debris, attest to the violence of the phenomenon. By analyzing microfossils and trapped organic materials, researchers have been able to precisely date these deposits, which coincide with the time of the Storegga event. Geochemical variations confirm a sudden and massive event. These clayey turbidites provide tangible proof of the tsunami, testifying to the profound disturbance of the seabed. By comparing these layers to coastal deposits in Norway, specialists have confirmed the event's date. The scale of the displaced volume illustrates the regional impact of the landslide. The analysis also reveals secondary fractures, signs of an unusually intense shock. The overall data suggests a rearrangement in multiple phases, reinforcing the idea of a major upheaval. Although the sea level was already rising, the Storegga tsunami accelerated the definitive separation between Great Britain and the continent. Mesolithic populations had to flee, taking their knowledge and tools with them. This exodus profoundly altered human settlement in northwestern Europe. For some researchers, this migration encouraged the emergence of new cultures, forced to adapt to a transformed environment. The catastrophe thus played a decisive role in the evolution of Mesolithic societies. After the retreat of the ice, the gradual rise of the seas isolated what would become the British Isles. The low plains were submerged, forming a body of water that cut off wildlife and human connections with the continent. This new archipelago, with its redrawn shores, saw many habitable areas disappear. The fragmentation of habitats first affected the large herbivores. The ancient fallow deer, a robust cervid dependent on humid forests and open grasslands, found itself surrounded, unable to migrate. Deprived of suitable territories, it declined rapidly, eventually disappearing locally, permanently altering the ecological balance of these island lands. The insular isolation did not only have negative effects. For some small mammals like the red vole, it provided an evolutionary advantage. Deprived of predators, this rodent spread widely and saw its population grow. The lack of contact with its continental counterparts favored the emergence of a distinct lineage, highlighting the role of insularity in species diversification. On the newly formed coasts, marine winds sculpted an Atlantic dune landscape, quickly colonized by salt-resistant grasses. These dune belts protected lagoons rich in amphibians, aquatic invertebrates, and colonies of seabirds, such as gulls. As the coastline stabilized, wetland areas called slacks developed between the dunes, fostering a unique biodiversity. Terns, shorebirds, and rare species of invertebrates found refuge there, permanently redefining the littoral face of the English islands. For human populations, these upheavals imposed a profound readjustment. The hunter-gatherers adapted their routes, focusing their efforts on wetland areas and marine resources. Fishing became essential, and simple boats allowed them to maintain, for a time, exchanges with the continent. But this isolation soon became permanent. When the Neolithic spread from the continent, it found a favorable environment here. Moderate temperatures and regular rainfall favored cereal crops. The raising of cattle and goats encouraged lasting settlement. Agriculture quickly took hold, favored by the richness of the soil. The islanders developed original pottery and funerary monuments, such as the first dolmens, rooted in a cult of the nurturing earth. Without marked external rivalry, their societies evolved freely. Maritime exchanges brought new tools, but without hindering the emergence of a cultural identity unique to the islands, now fully autonomous. progression of agriculture reshaped the environment, reducing forests in favor of fields and meadows. This opening of the landscape intensified interactions between humans and wildlife. While some rodents thrived thanks to cereals, a new ecological balance was established, reflecting the joint adaptation of humans and animals in an increasingly culturally shaped insular world. Throughout this process, the British archipelago forged its island identity. The extinction of the ancient fallow deer testifies to the fragility of large herbivores, while the red vole embodies resilience in the face of isolation. The coasts, sculpted by dunes, still harbor a great diversity. The Neolithic already reveals a genius of adaptation. England was born insular and turned towards the sea. The growing isolation of the British Isles shaped an imagination where the sea appears alternately as a barrier and a refuge. Faced with the constraints imposed by their environment, the inhabitants developed rich oral narratives, evoking submerged lands and mythical creatures. These legends, preceding writing, testify to an intuitive understanding of geographical changes. Archaeology confirms this evolution by the presence of everyday objects linked to a gradual sedentarization. It is in this tension between land and sea that an insular identity, still perceptible today, has been anchored. To understand the evolution of submerged landscapes like Doggerland, Beringia, or Zealandia, researchers today rely on cutting-edge techniques. They analyze DNA preserved in sediments, study the isotopic composition of elements such as strontium and neodymium, and map the seabed using 3D bathymetric LIDAR. These complementary approaches allow for the reconstruction with unprecedented precision of ancient ecosystems and their transformations over millennia. Sedimentary DNA corresponds to genetic fragments of ancient organisms found in layers of soil or sediments. Although often damaged, these microscopic remains provide valuable clues about the species that inhabited a given environment. With current sequencing techniques, it is sometimes possible to go very far back in time, up to several tens of thousands of years, to reconstruct the composition of biological communities. To access ancient DNA, researchers conduct coring in sediments, often in wet or underwater environments, where preservation is better. In the laboratory, samples undergo precise protocols to isolate DNA strands, which are then sequenced. These analyses allow for the reconstruction of extinct flora and reveal the presence of previously unknown animals. Thanks to this technique, it is now possible to trace life on lands that are now submerged. There are traces of trees, herbaceous plants, or mammals found buried under several meters or yards of water. These data shed light on the effects of climate and rising waters on the gradual disappearance of ancient terrestrial ecosystems. Isotope geochemistry, focused on strontium and neodymium, allows for the exploration of the origin and evolution of certain ancient materials. Strontium accumulates in teeth or shells, while neodymium is found in rocks and sediments. By comparing their signatures, one can trace animal migrations or understand the history of marine deposits. This method relies on the analysis of isotopes, versions of the same element with a different atomic weight. Their proportions reveal changes related to continental drift, rock erosion, or ocean circulation. In submerged areas, these data explain the unusual composition of certain sediments and reveal their ancient origins. "3D bathymetric LIDAR offers a spectacular view of underwater reliefs. This technology sends light pulses toward the seafloor and measures the time taken for their return. The reflected signal allows for the reconstruction of a highly detailed map of the submerged landscape, revealing ancient riverbeds, fossil dunes, or even human structures. Unlike acoustic systems, LiDAR uses light, offering better resolution in clear waters. Drones or airplanes fly over the areas to be mapped and send these beams. The return speed varies according to the depth and nature of the seabed, providing a remarkably accurate 3D representation. LiDAR has precisely located ancient riverbeds in regions like Doggerland or Zealandia. By comparing these surveys with sedimentary DNA analysis and geochemical isotope studies, researchers can reconstruct areas where human habitats and biodiversity intersected. This cross-disciplinary approach helps to better understand the structuring of ancient landscapes and the relationships between the environment and prehistoric societies. Each approach brings a piece of the puzzle: living species, the origin of materials, and the landforms. By combining them, researchers gain a comprehensive understanding of vanished ecosystems and the natural forces that shape them. Many laboratories, in partnership with universities and institutes, are perfecting these techniques. They are improving ancient DNA extraction to limit contamination and recover better preserved fragments. Isotopic protocols are gaining sensitivity, detecting subtle chemical variations. Meanwhile, LiDAR sensors are becoming lighter, more robust, and more precise, facilitating their use over vast coastal areas. Submerged lands like Zealandia, Beringia, and Doggerland bear witness to various mechanisms of disappearance. Zealandia sank slowly due to thermal subsidence, Doggerland disappeared rapidly with rising waters, and Beringia was primarily influenced by sea level. These transformations, very different from one another, occur over specific timescales, ranging from several million years to a few millennia. Zealandia vanished underwater due to thermal subsidence, a gradual sinking of the continental crust, linked to cooling after a period of intense activity in the Earth's mantle. Isolated from the rest of the world, this continent's fauna and flora evolved in isolation. This slow phenomenon, spread over millions of years, occurred without any sudden event. Doggerland experienced a much more rapid disappearance caused by a eustatic rise in sea level, meaning a global rise in ocean levels due to the melting of ice caps. At the end of the last glacial period, the massive melting of European ice caused a rapid rise in water levels. This submerged these vast plains connecting Great Britain to the continent in just a few millennia. This rapid submersion exceeded the adaptive capacity of many Mesolithic animal and human species. Fauna and populations were forced to retreat inland, following the inevitable recession of the shores. Beringia, between Asia and North America, was exposed during glaciations when ocean levels fell due to water being stored as ice. This land bridge allowed the migration of many species, both human and animal. Unlike Zealandia, the changes in Beringia were not due to tectonics or volcanism, but to the eustatic rise of seas after the last glaciation. Located at low altitude, the area was submerged by melting ice and rising temperatures, leading to the permanent disappearance of this migratory corridor. When observing the current fauna and flora around the world, one is struck by the unique development of certain species in isolated regions. These surprising distributions often find their origins in ancient events, continental separations, formation of land bridges, or marine submersions, which have shaped today's biodiversity. New Zealand perfectly illustrates this process. Isolated for millions of years, it has seen the emergence of a multitude of unique species. Among them, the tuatara, a reptile related to lizards, but belonging to a very ancient group, dating back more than 200 million years. Equipped with a vestigial third eye on the top of the skull, it bears witness to its primitive origins. Today, this discreet reptile survives only on a few islands or in protected sanctuaries where conservation efforts ensure its survival. Another striking example of New Zealand endemism, the giant weta, a massive insect that can weigh as much as a small bird. Belonging to the family of orthopterans like grasshoppers or crickets, it stands out because of its exceptional size. This characteristic is partly explained by the historical absence of terrestrial mammals, which allowed it to occupy several ecological niches without predation pressure. Giant weta live hidden, often in crevices or under bark, and come out at night to feed on plants or small invertebrates. Their nocturnal behavior makes them discreet, but also serves as protection against invasive species, such as rats. These singularities are largely explained by the position of New Zealand on the continental fragment of Zealandia, detached from Antarctica and Australia several tens of millions of years ago. As Zealandia partially sank under the ocean, the emerging lands forming the current archipelago remained isolated, limiting the arrival of competing species. This separation allowed local fauna to evolve autonomously, giving rise to unique, sometimes very ancient, lineages. In contrast, some land passages have facilitated the spread of species over vast territories. The Beringian Bridge, for instance, allowed mammals such as caribou or reindeer in Eurasia, and hares to migrate between Asia and North America. During glacial periods, sea levels dropped, transforming the Bering Strait into a wide snowy corridor between eastern Siberia and Alaska, facilitating genetic exchange between populations. As they moved, these Arctic herbivores colonized the tundra and the cold steppe, environments perfectly adapted to their diet. This is how Alaska's caribou and Scandinavia's reindeer, descended from the same ancestor, conquered the northern hemisphere. When the climate warmed and the waters covered Beringia, these populations were separated while retaining similar biological characteristics. Their dense fur and metabolism, optimized for cold, illustrate a close adaptation to the rigors of glacial cycles. In other regions, the submersion of ancient lands has left more subtle traces. Doggerland is a striking example. As the glaciers retreated, the North Sea gradually engulfed this territory, forcing terrestrial fauna to migrate or disappear. However, certain aquatic species survived and still inhabit Europe's rivers. The European eel is a fascinating testament to this. This catadromous fish, which is born in the sea but grows in freshwater, undertakes a remarkable migration from the Sargasso Sea to European rivers. In its larval state, it drifts over long distances before traveling upstream to develop. This strategy, according to researchers, dates back to a time when the seas and basins were configured quite differently. The lamprey, a primitive vertebrate without jaws, sometimes feeds on the blood of other fish. In its larval state, it remains buried in sediments, absorbing organic matter before migrating to the sea to become an adult. It then returns to the rivers to reproduce. This ability to live in very different environments has allowed it to survive marine upheavals. Its strange silhouette, reminiscent of an eel, intrigues scientists. Many consider it a living witness to our distant marine ancestors. These examples show the many ways life adapts to changes. In New Zealand, isolation has allowed the tuatara and the giant weta to retain very ancient traits. In the far north, the Beringian land bridges facilitated the spread of species like the caribou and the Arctic hare across two continents. And despite the submersion of Doggerland, The current presence of the European eel or the lamprey reminds us that some species have survived and keep the memory of a world submerged by the sea. Understanding this past allows us to better protect biodiversity today, a vital treasure for the planet's balance. Preserving these rare species, resulting from millions of years of autonomous evolution, also means passing on a fascinating, often unknown, genetic heritage. Oral traditions keep the trace of geological phenomena long misunderstood. In New Zealand, Maori memory speaks of Hawaii, an ancestral land beyond the seas, considered the birthplace of the Maori people. Passed down by the elders, this legend refers to an origin place now lost. For some specialists, Hawaii echoes the submersion of distant islands once connected to Zealandia, this partially submerged continent. In Polynesian tradition, Hawaii designates both a land of origin and a spiritual place. Some see it as a metaphor for the journey of the soul, others as a memory of a geological past. For millennia, Zealandia housed fauna and flora, evolving in relative isolation. Its forests, populated by tree ferns and podocarps, could correspond to the lands evoked in Maori chants. Found there, and still found today, are endemic species like the giant weta or the tuatara, living relics of an ancient world. In some subtropical regions, temperatures of around 77 to Jargo, sun 25 Liceo, would have favored lush ecosystems, fueling the imagination of a fertile and radiant land. Among the Chukchi people of northeastern Siberia, myths related to the land of Amak evoke an ancient isthmus, now disappeared, that once linked lands, now separated by the sea. This ancient passage, often identified as the Beringian Isthmus, would have allowed reindeer, wolves, and brown bears to move freely during glacial periods. The elders speak of vast plains swept by the cold, populated with hardy grasses, where temperatures often remained below zero. These narratives, passed down from generation to generation, retain the memory of a vanished world, with geography quite different from what we know today. For the Chukchi, Amak is sometimes referred to as a lost land, filled with heroic tales. There are stories of ancestors fishing in abundant rivers, but also of tragedies linked to rising waters during the post-glacial warming. Scientists confirm that at that time, much lower sea levels revealed vast lands, enabling human migrations to America. With the melting ice, these natural bridges were submerged. Amak thus became a fragmented memory, blending human history and geological upheavals. This oral memory illustrates the deep connection between culture and a changing environment. In the West, Celtic traditions evoke a submerged land named Cantrair Gwaelod, located in Cardigan Bay, off the coast of Wales. This fertile kingdom is said to have been lost due to the negligence of a ruler, causing a sudden flood. Some legends speak of dikes, meant to protect the plain, but an incident supposedly led to the submersion of the entire West. For several specialists, this myth could echo Doggerland. Although the locations differ, the stories share a common ancient memory of lands lost beneath the sea. In Celtic traditions, creatures associated with these lost lands sometimes take on a fabulous guise, threatening sea monsters, giant animals populating immense plains. Some myths mention deer with impressive antlers, similar to the megaloceros, as if they were trophies of a legendary hunting world. The ancient songs also speak of abundant waterbirds, testifying to the richness of a vast wetland area. And while poetry embellishes the facts, it nonetheless aligns with scientific discoveries. In the Paleolithic and Mesolithic periods, Doggerland indeed housed elks, fallow deer, migratory fish, and large forests of pines and birches. Whether they come from New Zealand, Siberia, or Wales, the legends of Hawaii, Omak, or Cantre'r Gwaelod all tell the same story. Fertile lands swallowed by the ocean. Behind the poetic figures, we find the memory of a broken link between humans and their nourishing land. These narratives, whether they evoke sudden tsunamis or slow rising waters, seem rooted in a tangible geological reality.